so much for the general theory on the movement. I think I will come back to this this exercise of yours, that the movement without forces is geodesic. Because to tackle geodesics, you have to apply another theory, and it's the calculus of variations. And it has to do with analysis of functions, and this is analysis in an infinite dimensional space. So we will come back to this, maybe already next time, but this is just the place to pose the question, to exercise. To solve it comes after. I think now is the place to repair the proof or the theorem I messed last time, and to finish up the catenary, which we did only in the theoretical aspect, but not quite. There is a practical aspect I would like to tackle now. Okay, so okay. Well, we have proved a simple theorem first, and that proof was correct, of minimizing V on M defined by G equals to 0, and we know that this had to do with looking at the Lagrange function. So many functions and equations carry the name of Lagrange, but there is no help for this. He did so much. L being equal to V plus lambda A dE. And we prove that if somewhere dV of x0 is equal to 0, well, no, that if the L of x0 is equal to 0, and also for lambda equals to lambda 0. Usually you don't write it, but the lambda is also a solution, a part of the solution of this equation. You should put it here. Well, let me do it. L of 0, lambda 0. This is x here, and this is lambda. Is 0, G of x 0 equals to 0, and d2 of x0 lambda 0 positive definite, then and if the omega, where all this is defined, is convex, then x0 is unique minimum. That was easy. Now, the general theorem says, consider this on a region omega and manifold M defined by G and GB regular now. M, V, G as above, and G regular. And if x0 gives a local minimum to V on M, then GL x0 lambda 0 equals to 0 for some lambda 0, and D2 x0 lambda 0 psi t psi larger or equal to 0 for R psi from the tangent space. That's the first part. The converse is, if this is true and this is positive for all psi tangent different from 0, then the minimum is strict. If strict inequality, then strict minimum. And we started the proof, which I repeat now. We consider the function we had of alpha being equal to V of P of alpha. And this function now, P parameterization, P around zero, such as P, I think I would put just alpha is equal to 0. Is equal to 0. Now, what this means? It means that now we have a simple smooth function of omega 1 alpha P alpha. This is the region of parameters. It comes with the definition of the parameterization. So now that means that your function V hat on omega 1 is a smooth function with a minimum at 0, which means first d V 0 is equal to 0 and d 2 V 0 positive semi-definite. It's a classical theory. So now comes the calculation. Yes. D2V or alpha j alpha L is equal to d over d alpha L. First derivative is the sum over I dv dxi dpi over d alpha j. Always taken at proper points. I don't write them down. It's a chain rule in the standard way. And now differentiate once more. You get sum over I and k, second derivative of v, well, no, v dx I dxk partial pi over alpha j, that's this, times pk over alpha L. That's the differentiation of this part, and then comes this part, plus this is a simple sum now, I dv over dxi, now the double derivative of pi over d alpha j d alpha L. That's what it is. And that this should be positive semi-definite. Now, to this we add something which is equal to 0. And this is d2 g. Well, lambda p g hat d alpha j d alpha L. Well, g hat is again the same thing. G hat of alpha is equal to g of p of alpha. But that's 0. That's an identical 0. So all derivatives are 0. That gives sum over yes, I will just repeat this computation here, put lambda hat g instead of v. It is the same formula. I, k, lambda t d2 g I g over d x I x k dpi d alpha j dpk over d alpha L plus sum over I lambda t d delta g over delta xi d2 pi over d alpha I alpha L. Just the same as above. So now you can add this. You get still this here, but you now can add this and you get the following. And now take alpha equals to 0, and that's where we are looking for it. Now, if you add this, then look what happens here. You have here the same expression, but now in the expression yourself you have dv over dxe plus lambda t dg over dxe taken at alpha 0, but that's 0 because this is the equilibrium point, this is the stationary point. So this can be crossed when you sum up. So you get the following now. Sum over ik. Well, this is now d2l over dxi dxk dpi over d alpha j dpk over d alpha l. That's what we have. And that's the fundamental equation here. That can be written down as dp t over d alpha I to L dp over d alpha j alpha L. All taken on the point alpha 0. Don't forget it. Here you have x0 and here you have alpha 0. Everywhere. Up there, here too. So now I can write down following to make it even simpler. I write B equals to sum beta A d pi dp over d alpha I. I represent any vector from the tangent space, that's the big B, by its components with respect to the basis of the tangent space. And now, this looks like this. Beta t d2 v beta equals to forms are equal only. You know, this is for every b from the tangent space, and this is just for every beta. And this correspondence is 1-to-1. So you see the positive non-negativity of this, of course, means non-negativity of this. But now you can do also the converse. If this is strictly positive, that means positive or non-vanishing vectors from the tangent space, that means that this is positive for all vectors beta different from 0. And that's positive definiteness. And that means unique minimum, unique local minimum, or as we say, strict minimum. Yeah, that's the same thing to say. And that proves the theorem. So this is, just the best equality you should somehow memorize. That you see that positive definiteness of a matrix is a matter of quadratic forms. You shouldn't look at a matrix by its elements. If you think of positive definiteness, you should think of something different. And this is quadratic forms which are produced by the matrix. And those forms correspond nicely. Now, somewhere. Now, along these lines, we will next time try to make our linearization in general case. Which still remains to do, I will not have time to do it more, is to finish my treatment of the catenary, where I had also to do with you one solvable case. You remember this difficult case with two springs, where we proved quite a lot of things, but we are not able to give you any general recipe to get at a solution. In general, you must just make try and error, or use some extra information you may have. But even such simple example gives you no general rule. Do it 1, 2, 3, and you have solution. No. Now, it's similar with the catenary, quite similar, even more difficult. But if the catenary is symmetric, then you can do it just almost the same way as with two springs. Maybe you remember, if we had symmetric springs, then we could reduce the whole problem to one-dimensional one. Two movements just on the vertical line. It will be similar in the catenary case, even more striking, because here you have quite a lot of variables, and we will be able to reduce the whole thing to a problem with one variable alone. And that, I think, is simply too much for today. And I will close now. Thank you.